Okay, please go ahead. Xuan, please go ahead.
Okay, yeah. Hello, everybody. It's a pleasure for me to welcome Professor Andrea Young from UC Santa Barbara as our first condensed matter seminar speaker for the semester. So Professor Young got a PhD from Columbia University under Professor Philip Kim in year 2012. Actually, just actually some years earlier, Philip was also on my thesis committee at Columbia, so that's a connection there. Yeah, so Andrea did a lot of groundbreaking work on graphene and the related 2D systems. So I found it very interesting, so I invited him to give a seminar here. Actually, he got a lot of prize for his seminal work, and which I will not spend much time listing here. So today he will talk about magnetism and superconductivity in ABC trilayer graphene. Andrea, please go ahead.
All right, thank you. Yeah, thanks for the opportunity to present some recent work. So I'm going to talk about some very recent things. Everything I'm going to talk about, you can find details in these two archive postings from my student Xuan Zhou, who's responsible for really most of this work. Let me start with just some very basic facts. So in condensed matter physics, or at least the brand of condensed matter physics that I am most interested in, the sort of basic question we have is, what can happen in strongly interacting matter, in particular when correlations between electrons become more important or equally important as, let's say, the correlations between electrons and the ions in a crystal lattice. And you can basically tie, the control knob that we have in materials that I'll show you is most basically we can control the density of states. And this turns out to be the useful knob because high density of states is the harbinger of correlated electron behavior. And the reason for that is that at a single particle level, when you have a high density of states, it means that there's essentially a large quasi-degeneracy between different states. If you have some finite density of electrons within, let's say, some Van Hove singularity or some other situation where the density of states becomes very large, then there's a large quasi-degeneracy, and that means that correlation energy scales can become important. And actually, you can see this already in at this point, very old types of physics where correlated states emerge, in particular, let's say, magnetism and superconductivity. So, for example, if you ask about magnetism in metal, typically people talk about the Stoner criterion. The Stoner criterion basically says that when the density of states, which is rho here, times the Coulomb repulsion becomes about 1, in other words, if the density of states gets large enough for this to be 1, then that's when you expect symmetry breaking in magnetism. Okay, so it just gives you a sort of estimate for when magnetism would come about. And in unrelated physics, BCS superconductivity, the formula for transition temperature in a typical BCS superconductor, actually this is not exactly for a typical BCS superconductor, I'll come back to that at the end, but let's say in an anti-adiabatic BCS superconductor, but it's true also for regular BCS superconductors, depends on the dimensionless coupling lambda, which describes the coupling between electrons and phonons. G is the dimensionful electron-phonon coupling, but rho is the density of states. So again, you get a higher transition temperature in a BCS superconductor when your density of states is sufficiently large. In other words, if you're at some temperature T, you'll generally speaking observe superconductivity as long as your density of states is large enough. And this basically all comes from the fact that in order to build in the correlations that lead to superconductivity or symmetry breaking as occurs in magnetism, this is going to cost kinetic energy because you're no longer going to be filling states in your band structure the way your single particle bands would have them, but instead you will you can build in these other correlations, and that energy cost becomes very small if the density of states is very large, because it means the energy difference between adjusting which states you fill becomes very small. Okay, so at a glance, graphene is very unlikely correlated material because basically its density of states is very low. So in monolayer graphene, you have very delocalized two-dimensional orbitals. And sort of as a result, they have a very low density of states. Their density of states actually goes like the square root of the density, detuned from the Dirac crossings that you get at the corners of the Brillouin zone. So I know there's at least one non-condensed matter physicist in the audience, because I recognize my old colleague Ben Monreal. So what you're looking at, I know for many condensed matter physicists, this graphene band structure is very familiar by now. It's something that gets taught in most intro condensed matter classes because it's a rather clean way to illustrate band structure concepts. But for his benefit, the basic physics here is that in monolayer graphene, your low energy band structure consists of these two inequivalent Dirac cones, where the elementary excitations are described by these massless Dirac fermions, where rather than the physical electron spin, you have a kind of pseudo spin that's related to the relative phase of the electron wave function on the two inequivalent sites within the graphene unit cell. So you can work through what the two-dimensional density of states is for this type of dispersion and find that it goes like square root n. It's very small, and that density of states is small, and you generally don't expect very strong correlated electron physics. Now, most of what I'm going to tell you about, you can basically understand from a very simple addition, which is if you think about the continuum between monolayer graphene and graphite, the most essential thing that happens when you add a second layer is that now electrons can tunnel between these two layers. And what happens is that that tunneling actually changes the band structure. Here I'm showing a zoom in of the band structure in the vicinity of these K points once you've added a second layer to make Bernal bilayer graphene. It's just two layers of graphite. And now you get something different, where when you apply an electric field in particular, you're going to get a density of states that actually diverges as you get close to the band edge. So now you have the situation where you have a divergent density of states, and you can hope that in fact you'll get all this correlated electron phenomena, because you're finding a way to sort of artificially increase the density of states and make it large enough that you will get interesting behavior that's not described by simple single particle band filling picture. And in fact, shortly after the first experimental isolation of bilayer graphene, it was predicted that, okay, if you dope it to low densities, close to this Van Hoff singularity, you should get indeed ferromagnetism, and maybe there have even been claims of theoretical claims that it should be a superconductor of various types. And actually, we looked for this, 5 years ago or so, and we didn't really see anything. In fact, if you look at this is a measurement of the capacitance of two gates, and I'll get back to this a bit later, where you're measuring the electric field that penetrates through a bilayer graphene layer at 0 applied electric displacement field and at large applied electric displacement field. And what you see is a basically well captured by the single particle picture. So what you're looking at here is that as a function of the charge carrier density, you see a big peak at charge neutrality when you have a large displacement field. That comes from the fact that you have a gap. So there the electric field will penetrate through this two-dimensional layer. But right next to it, you have these deep dips. That's where the system has very high density of states. And in a sense, it's telling you that nothing really interesting is happening. I'll revisit that a bit later. But the hypothesis that this talk starts from is that actually this is a matter of degree and not of kind. In other words, for whatever reason, the density of states in bilayer graphene is simply not quite big enough for anything interesting to happen. The Stoner criterion is a relatively sharp boundary where you get a first order phase transition to a magnet, and TC in a superconductor is exponentially sensitive to the electron phonon coupling and therefore the density of states. So it's certainly possible that all of that physics does indeed manifest in these types of systems, but doesn't manifest in this particular system. And in fact, this seems to have been borne out already before we started this work by a few works that started to see signatures, let's say, of correlated electron physics in rhombohedral graphite of various types. Okay, and so you can see this by looking at, let's say, the simplest, a two-band model for the low energy physics near the charge neutrality point in bilayer graphene and ABC trilayer graphene. So that the idea here is that actually it turns out that, you know, as you build up stacks of graphite, but not conventional graphite, rhombohedral graphite. So in normal graphite, you have Bernal, you know, it's Bernal stacking, which means that if you have essentially three choices when you stack two layers on top of each other. You could actually stack them exactly the same, right, with each atom on top of each other. That's very high energy, so that doesn't really happen physically. But then you have a choice of whether you're going to put the second layer in one of two ways, where one of the two atoms in the unit cell will be on top of another atom in the first layer, and the other will be in the center of a hexagon, and you have two different ways you can do that. So in Bernal, the stacking order is A, B, A, B, so it goes back and forth between two choices and doesn't realize the third choice. But in ABC, it means you actually are going to realize the third choice every third layer. And those have very different electronic structures, but in particular, ABC, trilayer, and indeed rhombohedral graphites all basically resemble Bernal bilayer graphene in their in the schematic picture of their band structure. And you can see that from these low energy Hamiltonians, where the only thing that's changed is actually just the power to which this px plus IPY or px minus IPY operator is raised on the off-diagonal term. So their band structures actually look very similar. The only difference is that this Van Hove singularity, the divergence of the density of states is increased somewhat in ABC trilayer. Okay, you can look at more details. This is of what that band structure looks like within a model. Here are contours of the Fermi surface. This is when you account for not just the simplest model, but actually all the different ways that electrons can hop between layers and within a layer. So you get something much more complicated where you account for all 6 atoms in the unit cell. But the basic physics is the same, in that you have these divergences in the density of states, which are enhanced as you put a larger and larger electric field across these 2 layers. These Van Hove singularities also take on a little more the character of saddle point Van Hove singularities rather than band edge Van Hove singularities for those who are interested. But the point is that you can create the situation experimentally where you have very large density of states, and then ask yourself what happens. Okay, so we can look at this band structure in a bit more detail if you want. And here is a very low density, let's say, of holes. You'll start with 3 pockets. These pockets will then merge at a saddle point where the density of states diverges. As you further increase the doping of holes, you will form an annular Fermi sea, so you'll have a hole-like and an electron-like Fermi surface, and then eventually that electron-like Fermi surface will vanish, and you'll just have a simple hole-like Fermi surface. So that's the basic picture of what you'd expect from a single particle model of ABC. Okay, now the process of actually doing the experiment is not so trivial in ABC as compared to, for example, Bernal bilayer graphene, because ABC is not the ground state configuration of graphite. It's metastable and, generally speaking, will relax to an ABA stacking without a number of tricks. So to give you an idea of how we actually make these samples, we start off with, it's true that if you just exfoliate graphene, so the same way that everybody who studies high quality graphene will make it, you start from graphite and you exfoliate it onto a silicon substrate where you can look at it. You can certainly identify 3-layer flakes, and then using Raman spectroscopy, you can see that something like 5% of the total area of trilayer graphene flakes will be in this rhombohedral stacking order. And that rhombohedral stacking order, and those can be large. You can even find 100 square micron flakes that happen to all be ABC, but it's not a stable configuration. So in particular, if you have mixed domains of ABC and ABA, then in the process of either heating, which happens naturally when we do our exfoliation, or in the process of further straining it even at room temperature, which happens in the process of building up these van der Waals stacks that we need in order to do our experiment, there's a sort of built-in pressure between the ABA regions and the ABC regions. So that domain wall between those always has some pressure on it. It may be pinned, but it always has some pressure on it. And after normal fabrication, you will be left with only ABA, and you won't be able to study the material you actually want. So we developed a whole set of basically process improvements for stabilizing ABC. In particular, you can actually use you can cut graphite and graphene pieces out with a kind of selective oxidation using an atomic force microscope tip in a humid atmosphere. So you can cut out purely ABC flakes. That actually helps because that will prevent these ABC domain walls from propagating if they hit just an edge of a graphene flake. You do Raman spectroscopy throughout the process, so we design our whole process so that we can abandon samples that have already relaxed to ABA, and we develop some tricks for minimally manipulating these ABC flake. And so it fails often still, but one of the great things about this is that it tends to fail completely or not at all in the sense that once you stabilize an ABC, it's possible to stabilize a purely ABC flakes, and as you'll see, then these systems have extremely low disorder. And this is particularly in contrast to moire systems, which have been kind of in vogue the last few years, where you're really trying to stabilize a structurally unstable stacking order when you have a finite twist angle. That's not even metastable, it's simply structurally unstable. And what that means is that you're automatically stuck with whatever quenched strain you've managed to quench. There's no way to find a uniform state because, for example, 1.1 degrees, the magic angle in twisted bilayer graphene, is not special from a structural point of view. It's special from an electronic point of view, but it's actually less energetically stable than 1.09 or 1.11 might be again slightly different energy, but they're all more or less equally stable. But if you tried to make that a uniform system, you would end up with a Bernal stacking because that is the actual structural ground state of a bilayer. And of a trilayer also. So this allows you to actually stabilize a metastable and uniform state, and that actually turns out to be a feature more than a bug. Okay, so to give some idea of what these devices, what these devices are, how they're made, what's important here, these are coming after a sort of 10-year odyssey to improve the quality of these devices, and what I mean by quality is really just the reducing disorder of every kind, right? And in particular, disorder coming from charge and strain and corrugations and so on, which can afflict two-dimensional materials. So starting from the ideas of removing silicon substrates, then moving to single crystal two-dimensional materials as dielectrics. So in particular, all of our samples are made with hexagonal boron nitride dielectrics, which is a largely defect-free large gap insulator with the same basic structure as graphite. You need to have this on both sides. It actually turns out that these interfaces between graphene and hexagonal boron nitride have this wonderful kind of self-cleaning quality where they will form an atomically sharp interface, and as you manipulate them, any trapped hydrocarbons will actually move to the boundary and then don't get back in once that interface seals. So you can make very clean interfaces. And then more recently, just in the last 5 years or so, we really came to understand that actually the limiting factor was patch effect from deposited, sort of typically evaporated metal gates, and those metal gates had grains, and those grains have different work functions, and that was actually a leading source of disorder. So we moved to using single crystals of graphite as the gate dielectrics for these types of materials. And now we have these all van der Waals type of devices. And if you look, for example, at physics in the quantum Hall regime, which I won't discuss here, you can see that the sample quality is comparable to what you get in molecular beam epitaxy grown 3-5 semiconductors of the sort of highest quality. The measurements that I'll show you actually, and I showed you already, are for the start of this talk, are measurements of the inverse compressibility, or really they're measurements of the capacitance. So if you have a structure like this, you can measure the capacitance between one graphite gate and the other with the bilayer graphene grounded, and that gives you directly a handle on basically the thermodynamic compressibility, because if this is an incompressible state, so think about a system with a gap, then a small AC electric field on this graphite will simply penetrate because this bilayer cannot screen, whereas if it's a highly compressible state, then that electric field will be screened and you'll see no current on the top gate. And so mostly I'll be showing you measurements of this inverse compressibility, which is what this probes. And here is a measurement in high magnetic fields, and you can see these orange features are where the system forms an incompressible gap state, and light blue on this color scale is where the system is highly compressible. Okay, so let me show you the same measurement in ABC trilayer graphene. So I'm showing you data now plotted on a color scale as a function of the charge carrier density. So here's electron doping, and here for hole doping. All of this is just affected by changing the DC voltages on these gates, and displacement field, which is just the, here it's the voltage difference between the top and bottom gates, whereas the density is tuned by their sum. So you can change the total density. You can also change essentially the polarizing electric field. And we measure, and you can read this color scale as being proportional to the inverse compressibility. So the claim that I'll make is that almost everything you see here is some kind of magnetic transition in these low energy bands of ABC graphite. Okay, and there's some exceptions. So for example, there's a feature here that you can see that we can actually identify with the creation of an electron pocket in the whole Fermi surface that's well described by a single particle model. So you see that there's a step in the density of states and a step, therefore, in the inverse compressibility, and it lines up very well with where you expect to go from having Fermi surfaces that are simple to Fermi surfaces that are annular. And what I'm drawing here, and I'll use these schematics throughout, so let me just explain them, is that in graphene you generally have 4 flavors of electron. So because you have your sort of spin degeneracy, but then you also have the degeneracy between these inequivalent Dirac cones at the corners of the hexagonal Brillouin zone. There are actually 2 of them. So that gives you 4 spin and valley flavors that you can occupy, which are roughly symmetric, not perfectly. The wave functions are not exactly the same, but it's almost like you can think about an SU4 spin or isospin that emerges from the combination of those 2. And so when I draw these, what I mean is that in this situation, when we don't have any ferromagnetism, you have basically 4 pockets that are equally occupied in the different spin and valley isospin flavors, and then all of them undergo this Lifshitz transition where you nucleate a new Fermi surface inside the large Fermi surface. So you can actually try to map this out very precisely using quantum oscillations. So these systems are very clean. Their mean free paths are many microns. So even at very low magnetic fields, you can resolve oscillations in the resistivity plotted here, which probe the extremal area of a Fermi surface. And so then we can Fourier transform these, so we can, this is what a measurement looks like. So you can see even from, 100 millitesla, you start to see many oscillations in the resistivity, which develop and have various complicated features. And so you can plot this as a function of 1 over b, which is and then Fourier transform that. And then the plots that I'll be showing you, we're going to take those Fourier transformed frequencies and divide them by the total density. Okay, and the quantity that will be of interest to us is what we'll call F sub nu. And what this is a measurement of the fractional area of the Fermi surface enclosed by a given orbit in momentum space. So whenever you see an oscillation, that's corresponding to some orbit of a Fermi surface. It encloses a certain amount of area, and this is going to plot the fraction of the total area of momentum space occupied by your electrons. And that'll allow us to get a picture of the evolution of this band structure. Okay, so this is what it looks like, for example, at 0 displacement field. And I want you to focus in particular on what's going on here. So at large density, we indeed see one strong peak that is at F nu of 1/4. And that's exactly, and same thing for holes and electrons, that's exactly what I was describing before. You have 4 Fermi surfaces of equal area. Each of them is 1/4 of the total density, and that's it. That's the whole, that's everything that's going on. But now as we lower the density on the hole side, you see that actually this frequency starts to go up, and it's joined by a very low frequency oscillation that starts from 0. And that's, again, exactly the behavior you expect if you're nucleating an annular Fermi, if you have an annular Fermi C, so you've nucleated now an opposite charge Fermi surface. Now the difference between these 2 frequencies is going to add up to 1/4 because you still have 4 of them, and so on. Then there's more complexity. So at very low density, right, you actually see a strong peak at 1/12 of the total, and you can tie that to these 3 pockets in each of 4 flavors. So now you have some, 12 little Fermi surfaces related by a combination of spin, valley, and C3 rotation symmetry. Okay, and then you might have the beginning indications of a ferromagnetic state where now you have a strong peak right around 1/2. Okay, which means now that you actually apparently have 2 Fermi surfaces rather than 4. So that means you must have broken spin or valley symmetry, and you can see there's already an indication of that on the electron side in a particular instance. But all of this gets much more dramatic once you put large displacement field, which, if you'll recall, is really equivalent to making this density of states very large, because that piles up density of states right on near this band edge. And now we see a bunch of things that are very clearly coming from symmetry breaking. So in particular, one of the features that you see is these strong negative compressibility features where this compressibility, which is really just inverse density of states in a single particle picture, becomes negative. And that's not something that you can get from a single particle picture. It's typically associated with deviations from uniformity in your 2-dimensional electron system. And maybe the most obvious, what turns out to be the case here, is that's actually just, these are associated with first order quantum phase transitions tuned by the density, where, as I'll show you, you're going from states of one type of symmetry to a different type of symmetry. So in particular, a probe you can do then is to look at those same quantum oscillations, and you can do quantum oscillations. Let's take the electron side first. In these, there are 3 different regions here, you could say, at high displacement field, separated by these strong negative compressibility lines. And if you take a quantum oscillation measurement and do the same Fourier transform that I described to you in this 4-fold region, in this region here that I'll call the 4-fold region, you see a peak right at 1/4. But if you do it in this region, you'll see a peak at 1/2, and if you do it in this region, you'll see a peak at just 1. So this really means that here you have 2 Fermi surfaces, and here you only have 1 Fermi surface in the 0 magnetic field limit. That's where these are taken, at very low magnetic fields. And so what these negative compressibility features demarcate are breaking of the symmetry of the spins and or the valleys. That sort of question to be resolved. Okay, so how do we understand this? It turns out you can understand this very simply in just by taking a Stoner model. And what a Stoner model basically does is it says there's some energy that you get from just filling bands. So that's this first term. The second term is basically saying there's an overall chemical potential. So this is all grand potential in terms of this chemical potential. These are densities of different, the alphas are densities of different flavors. And then you just add a pretty much phenomenological exchange term that favors filling the same flavors. Okay, so it's not a microscopic calculation. It's pretty phenomenological, but it does account for the density of states through this E sub k is a calculation of the energy required to fill the single particle band structure. So this is going to build in some repulsion term, which favors occupying states of the same flavor. In this case, the alpha and beta are going to range over different spin and valley flavors, and the single particle density of states. Okay, and then so we can put that in for 0 displacement field where the density of states looks like this, or for large displacement fields where it looks like that, and so on. Okay, and we can do this with we can put in all the band structure details. It's of course notoriously difficult to really calculate well this Coulomb repulsion accurately, but we're just going to set it to be a number. Okay, and if we do that, we can see that the basic behavior of these features more or less is mimicked by the Stoner model, and that they don't do much at low density, and then they go out to higher density as you increase the magnitude of this Van Hoff singularity. So it captures the basic, density versus displacement field behavior. Interestingly, it gives you the wrong number of transitions. It turns out you can fix this, in a very natural way with a kind of Hund's coupling that, just as in a shell filling of an atom, you fill nominally degenerate states in a certain order because there's actually some difference in exchange between, spins and valleys, or spins and orbitals in this case. And experimentally, you can actually work out what that Hund's coupling is using the in-plane magnetic field dependence. And without getting into the details too much, basically what we can find is that this 1-fold phase is fully spin and valley polarized. The 2-fold phase is actually spin polarized, but valley unpolarized. And then the 4-fold phase is, of course, totally symmetric. Okay, so it's sort of a ferromagnetic Hund's rule coupling. And this is confirmed by measurements of the anomalous Hall effect, which is different in the two different valleys. And so if you have a valley unpolarized state, as in this twofold state, you'll have no anomalous Hall effect, but in the valley polarized state, you will have an anomalous Hall effect, which indeed we observe. Okay, so hole filling is much more complex. And as I'll show you, that complexity is not just for no reason. Should we try to understand it, because there's much more phenomenology here. But at the level of the ferromagnetism, it seems considerably more complicated because the band structure is more complicated. So in particular, you have much more strongly developed threefold pockets. The Van Hove singularity, where the density of states becomes very large, is at finite density, and then you have these annular, this transition between a simple Fermi surface and an annulus. And so you can try to work this out. This also seems like there are just stronger features on the whole side, stronger sort of interesting phenomenology. So for example, within this valley polarized 1x phase, you see a very strong anomalous Hall effect, which can become hysteretic. And actually, if you just tune the density, or as you just tune electric fields to cross these transitions between what we would say is a 1-fold spin and valley polarized phase and a 12-fold spin and valley unpolarized phase with 3 pockets in each flavor, you can actually see hysteretic switching of magnetic order just by an electric field, because you're just going across this phase transition. And so you can try to sort of work out, everything that's going on here using finite magnetic field capacitance measurements and zero magnetic field capacitance measurement, resistivity measurements, and so on. And basically, what you find is that there's a very sort of complicated, in and out between states that have Lifshitz transitions where you nucleate new Fermi surfaces, and also phases that are not completely spin and valley polarized, but rather are partially polarized within this set of flavors in the same way that most ferromagnets are simply partially polarized. They're not fully a half metal. If you take a piece of iron, there's some small spin imbalance, but they're just kind of partially polarized, and that's a tunable knob. So we can try to work out this fermiology, and we find that at high density, as I showed you before, you have 4 simple Fermi surfaces. At very across a cut here, you can see that there are regions where you have 2 simple Fermi surfaces, so something that has broken the spin or the valley degeneracy. As it turns out, that's already more complicated here than on the electron side. You have regions of annular Fermi surfaces, and then you have regions which we'll call partially isospin polarized, where you have a lot of spectral weight in these quantum oscillations, somewhere a little smaller than 1/2. You have a fair amount just above 0, and presumably these sum to 1/2. So you have maybe 2 large and 2 small Fermi surfaces, but it's a little hard to tell because the quantum oscillations there are quite complicated. They have a lot of, they're not as sharp or well-defined as they are in some of these other phases. Okay, and then this pattern tends to repeat, so you can go through this in a variety of other places where, again, you see now a half metal where you just have 2 out of 4 of the natural Fermi surfaces, a half metal with annular Fermi surfaces, a quarter metal where you simply have spin and valley polarization, a quarter metal with annular Fermi surfaces, and then additional partially isospin polarized phases, and so on. So why go through all of this? We can make this phase diagram, but is this just pointless zoology of this system? And at first we thought it was pointless zoology, and so we didn't think very much about it. But then, let me skip this. I'm going to go ahead and skip some of this part and just move on to talking about transport. So, why go through all this zoology with you at this point, right? There are these very complicated transitions in Fermi surfaces. One could say, okay, the basic takeaway is that the system is ferromagnetic. It turns out that if you then go back and measure transport, actually this zoology becomes considerably more interesting. In particular, if you now look at transport measurements, you find that the system is actually superconducting in a variety of different densities and dopings that are precisely correlated with some of these transitions in the Fermi surface. So I'll highlight, so this is now resistivity. sorry, the color scale is missing, but these cyan regions here and there are all superconducting. Okay, you can see this through the nonlinear resistivity dVdI, which drops either to 0 or very close to 0 at low temperatures. They're all superconducting sort of below 100 millikelvin. The weakest ones maybe only below 50 millikelvin. They all show this onset of nonlinearity and zero resistance or near zero resistance in the case of the least well-formed one, which grows with decreasing temperature. And they are all, as you can already see from transport, basically tightly correlated with phase transitions in this ground state, isospin magnetic order. Okay, so basically I'll tell you a bit of the state of knowledge of what we know about these superconductors and sort of what we're thinking about them. I'm not going to tell you the answer because we don't know the answer of where this comes from, but this is of course extremely low densities for superconducting states. Here, these are superconductors happening at 0.5 10 to the 12. That means basically if you think about putting those electrons, let's say on a triangular grid, that lattice spacing is on the order of 10 nanometers. There's really not very many electrons that are superconducting in a system with essentially no disorder at low temperatures, but obviously accessible temperatures to us. Okay, so let me try to go back and try to understand what's the fermiology specifically in these superconducting states, right? So here are resistance oscillations measured as a function of perpendicular field. This is basically data you've already seen, and now we'll just zoom in on the on this F nu measurement. And what you can see is there's this superconducting state. This is a measurement at zero magnetic field of the superconductor. So resistivity drops to 0 over some range, and we can just look at the fermiology of the normal state, right? Where apparently we have these annular Fermi surfaces. This is exactly in the situation of having 4 annular Fermi surfaces just before the transition to some isospin polarized phase. Okay, so the superconductivity happens on the side where the normal state Fermi surfaces are 4 annuli, just before you lose some kind of degeneracy and you see this jump from some 4 annuli to maybe 2 large and 2 small Fermi surfaces. Okay, but well before it becomes 2 simple Fermi surfaces. So can this be an unconventional superconductor, right? So actually the simplest, there's just as some background, right? Of course, everybody is familiar with the basic idea that superconductivity near a quantum critical point or near some kind of transition to an ordered state, there are many theoretical ideas for how this can come about. In particular, one could ask the question of can fluctuations of whatever this partial isospin polarization, whatever the order associated with that, could be mediating pairing in the proximal normal state? That's sort of a natural question to ask. One of the features of most, if not all, electron-mediated superconductors is they typically don't have conventional pairing symmetry. In particular, they're often not S-wave. In the cuprates, they're D-wave. And in many theories, you'll end up with other types of unconventional pairing symmetry. And a key fact about superconductivity in its conventional form is that when you have an S-wave superconductor, disorder doesn't really matter, right? Because the Fermi surface is uniformly gapped, and so even scattering across the Fermi surface by very strong disorder by Anderson's theorem is not going to degrade TC at all. And usually this is not true in unconventional superconductivity, where, for example, in a P-wave superconductor, conventional disorder behaves like magnetic disorder in a conventional superconductor. And that's basically described by Abrikosov-Gorkov, theory of disordered superconductors, where you don't need magnetic impurities, you just need regular impurities. So you can actually just assess whether it's plausible that this be an unconventional superconductor by asking, what is this parameter? And that's the ratio of the coherence length to the mean free path of the normal state, right? And so if this coherence length is much smaller than the mean free path, then you could have an unconventional superconductor. But if this is about once they get to be comparable, the expectation is any unconventional superconductor would be destroyed. So we can basically already test the hypothesis of, this is an unconventional superconductor. We could negate it by simply finding that superconductivity survives into the dirty limit. Okay, so how do you measure this? Well, the Ginzburg-Landau, coherence length, you can just measure from basically the critical out-of-plane magnetic field, and then that basically gives you that. And the mean free path you can measure basically from the mobility of the charge carriers. All right, so measuring psi is relatively straightforward. We simply apply an out-of-plane magnetic field, and we find that superconductivity dies on the order of 10 at fields on the order of 10 millitesla. And so you can extract a coherence length of a couple hundred nanometers, which is not, which is just a number that we can keep in mind. Okay. As far as L, the mean free path, we can think about what the normal state resistance is and its density. So that simple estimate gives you something on the order of a micron, which is already considerably larger than the estimated coherence length. But actually, there's a much more stark measurement that you can do given this device. So this is actually what the device looks like. It's sort of cut out in a funny triangular shape, but it has 4 contacts all along one side. And it turns out there's a simple experiment you can do here if you have ballistic electrons, where you drive a current you put a voltage between these two contacts. But in order for a current to actually end up at ground from this source, electrons have to follow ballistic trajectories, and in a magnetic field, they can be focused into the additional contact. So if you set up a measurement like this, current will relax by bouncing off some boundary, but first it will be focused into this contact where it will relax its energy and generate a voltage. And this is a resonant effect as a function of a magnetic field, and actually you can see the signatures of this effect right around the densities where the superconductivity occurs. And if you think about the device geometry of 2.5 micron or so spacing between these, this basically implies a mean free path on the order of 5 to 10 microns. So really quite large. This is basically a signature of ballistic electron transport with no scattering off of disorder inside this system. So we certainly are strongly in the clean limit in that the mean free path is much longer than the coherence length, and so at least on those grounds we can't immediately rule out an exotic form of superconductivity. We can check other aspects of what you expect for simple superconductors. So for example, in a spin singlet superconductor, you expect superconductivity to be destroyed when the Zeeman energy becomes comparable to the superconducting gap, because that's basically pair breaking. And within BCS, the ratio of that Zeeman energy to KB times the zero magnetic field transition temperature is something on the order of 2. And if you do this measurement, so now you can look at in-plane magnetic field dependence of superconductivity plotted here as a function of density. Just as before, you see that it survives up to several hundred millitesla. But that's actually rather consistent with the transition temperatures that are observed. So you can see that it's pretty good fit to this BCS formula. The value is something like 1.23, whereas in absolutely vanilla BCS, it's supposed to be 1.7. But these are, a survey of the literature suggests most superconductors don't nail this right on the head. This is not a very big deviation, and so we can basically conclude that probably the spin structure is spin singlet of this superconductor. Okay, so now let me move on to the sort of second superconductor, or the second of 3 superconductors that we observe, which actually happens in a somewhat similar but otherwise rather different regime. So in particular, here we're in the superconductor actually occurs in a situation where there's already full spin polarization. So that's a very unusual situation. So we can look at the quantum oscillations. So the superconductivity happens right here. Quantum oscillations in this regime show a half metal, so strong peak at 1/2, which means 2 Fermi surfaces that are simple. And then we enter a region where we have annular Fermi surfaces, but again, 2 of them. So you have a peak at low F nu and then a peak at slightly higher than 1/2 F nu, exactly as in the first case. And then the superconductivity seems to happen just on the border before you enter some kind of partially isospin polarized phase. Okay, so in many ways it's analogous, but except that now we're actually in a fully spin polarized metal. So we're in a half metal in the sense that we only have one projection of spin, and yet we have superconductivity. So certainly that is not a normal situation for a superconductor. And you can see that indeed this SC2, the second superconductor, violates the Pauli limit by a very large factor. So the transition temperature is less than 50 millikelvin, but you can essentially apply as large an in-plane field as permitted by our magnet and see no change, for example, in the out-of-plane critical field or the transition temperature. So even as 1 millitesla of out-of-plane field will destroy the superconductor, 1 Tesla of in-plane field has no discernible effect on it of any kind. So this is very clearly not a spin singlet superconductor, and that makes perfect sense because the normal state is a spin polarized half metal. Okay, so how can you have superconductivity in a half metal? Actually, it may not be so crazy in graphene. So you can consider, if you have an attractive pairing potential in every channel, usually S-wave pairing is the most attractive, and so most superconductors have essentially S-wave symmetry. But if you already start from a half metal, then you certainly can't have spin singlet pairing. You don't have the other spin. A way to think about this is that exchange is very strong. Spin flips are separated from the ground state by some energy scale that might be 5 millielectron volts or 50 Kelvin in the scale, but the superconducting gap is only 10 microelectron volts, so not very big. So the thing about why this usually that means you just don't get any pairing. Most ferromagnets don't have any pairing. The basic reason for that is there's no obvious way to make. There's no you don't have a Kramer's degeneracy anymore. You don't have obviously degenerate electronic states from which to construct your Cooper pairs. But in graphene, that's actually rather special because in addition to not we don't have inversion symmetry as often happens in ferromagnets. And therefore no obvious pair that's degenerate, but we also don't have spin-orbit coupling. And so what this means is that you can have spinless time reversal symmetry between electrons in the different valleys. So that's a natural way to then make a superconductor, just to forget about spin and let's just call valley our new spin, and then you have a superconductor where you pair states of opposite momentum in opposite valleys, right? And those are sort of guaranteed to be degenerate by the absence of spin-orbit coupling. And in this situation, you can actually get something that's very similar to, it would be a spin triplet, but valley singlet superconductor. And in many ways, it would be rather similar to a conventional superconductor. So that might be what's happening. So, okay, so let me conclude with just telling you sort of what we think maybe, what are some constraints on the mechanism and what are the obvious next experiments. So I think, certainly this question of, can it be fluctuations? I think that it could, right? It's true that, the transition in quantum oscillation seems rather abrupt, right? And you might expect a fluctuation mediated superconductivity to be occurring where you have a second order transition. On the other hand, it's not so abrupt as other transitions. So there are other transitions that actually show hysteresis where you clearly have a very first order transition. This one does not have hysteresis and generally speaking seems about as mild as any of the other isospin symmetry breaking transitions we've seen. So it could be second order. This is something that we could check. So fluctuations or not, I don't think we can exclude that as a mechanism at this point. There's some constraints. This is maybe a little bit for the experts at this point. In particular, who are into sort of the details of these graphene systems. But one thing we know about the phase proximal to the first superconductor, it is not a spin polarized phase. So the transition is between a spin unpolarized metal and then some kind of spin unpolarized, ferromagnet. It may be something perhaps where it develops spontaneous coherence between the two valleys, and there's later a transition to a spin polarized set of phases. So the constraints on a theory, I think, are relatively clear, which is that you need to generate something that seems to be a spin singlet superconductor from some unconventional pairing mediated by fluctuations of a spin unpolarized magnetic phase. That's a challenge for theory. I'm sure that it can such a scenario can be cooked up. But let me talk about, maybe if there's a way to reconcile all of this pretty spectacular phenomenology with like a really simple what's the simplest thing that can happen, right? And the main issue with thinking, okay, can this just be a regular phonon-mediated superconductor? There are a couple of issues. So actually, one issue is that you're at extremely low electron density, right? So that's very different than typical superconductors, where in typical superconductors, your Fermi energy is very large compared to the Debye temperature. But in this superconductor, that certainly wouldn't be true. Your Fermi temperature is actually very small. But that turns out to be okay. There are a number of, the theory of anti-adiabatic so-called limit superconductivity was worked out, I think, mostly by Gorkov. And you will get BCS superconductivity also in this limit. Rather than omega Debye times some exponential factor, it's T Fermi times some exponential factor. That seems very reasonable here. But there's a bigger sort of issue, which is, why does superconductivity occur at a symmetry breaking transition if the symmetry breaking and the superconductivity have totally different origins, right? If one is coming from electron-phonon coupling and the other is coming from electron-electron repulsion, why are they coincident? Why isn't it superconducting all the time? Why is it ever superconducting? Why does it only seem to happen at these magnetic phase transitions? Okay, and I think there's actually a relatively elegant synthesis of those two things, which I previewed in the first slide of this talk, which basically is just the fact that both magnetism and superconductivity happen when the density of states becomes large, right? Both of them, in a sense, are giving you some critical density of states above which something interesting happens. We can call one of them, rho ferromagnetism and the other rho superconductivity. And even from unrelated mechanisms, then, it's not unexpected for these things to coincide. So the picture here would be to say, all right, let's take some different cases, right? Let's say that you have, the critical rho for ferromagnetism is smaller than the critical rho for superconductivity. What I'm plotting here is density of states per flavor as a function of electron density. And along this yellow line is when you have no symmetry breaking. So as we reduce the density of holes, in this case, towards 0, which is over on the right side, we reduce it, the density of states goes up as we approach this Van Hoff singularity until we hit rho ferromagnetism, right? And when we hit rho ferromagnetism, we then break the symmetry, right? So now we break the symmetry, we go to half, the number of occupied flavors. The density of states goes down, and you never get to rho superconductivity, because every time you break a symmetry, your density of states goes down, and then you repeat this process. You continue up and down these curves until all symmetries are broken, and once all the symmetries are broken, you actually can't pair anymore because you don't have any sort of degenerate electron states from which to make your condensate. Okay, so that's one situation where, if rho ferromagnetism is lower than rho superconductivity. But what about the other situation, right? If in the other situation, you're going to decrease your density until you reach rho superconductivity, and now you start seeing superconductivity, okay? And now it superconducts, you keep lowering your density, right? You're still in a symmetry unbroken state, and you're gonna superconduct until you hit rho ferromagnetism, in which case now you have ferromagnetic transition, density of states goes down, superconductivity is destroyed, and that seems rather similar to the experimental situation, that you have a range of superconductivity proximal to a magnetic transition, but actually they don't have anything to do with each other, right? They're just competing phenomena, and it's just by virtue of the fact that you're increasing density of states along these trajectories that this occurs, that they occur next to each other, right? There's some quantitative issues with this that we're still trying to think about, right? Which is that if you just look at the simplest picture here and ask, how much does TC change over what range of density? It doesn't quite make sense, in the sense that it's surprising that if this is true, the density of states is not changing so rapidly that you wouldn't expect superconductivity basically to be much more ubiquitous than it is. We do see it over a relatively narrow range, but it comes down to some details of how correct is this formula, what things are missing, the Coulomb repulsion is not accounted for, and all these other things which we know are important. So it's not clear. Clearly going to lower temperatures, and if superconductivity remains pinned to these transitions, even at the very lowest temperatures, that would suggest that in fact it's something related to the transition, but we don't quite have the dynamic range of temperature relative to TC at this point to really be able to tell. one more anomaly that I'll present just as food for thought is that at high temperatures, very little happens. In other words, we can increase the temperature here above the superconducting transition. This is again as a function of density, and the resistivity really doesn't do very much. It sort of stays about the same up to 20 Kelvin, and that is surprising because the same type, if you have scattering off of a particular bosonic mode, let's say a phonon or some kind of appropriate magnetic excitation, the same things that might lead to some attractive pairing at low temperatures typically give you some scattering in the normal state. So, if you look at aluminum, aluminum of course has electron-phonon scattering at high temperatures, and actually the dimensionless electron-phonon coupling you extract from that high temperature behavior is the same as the electron-phonon coupling that shows up in the BCS formula to within 20 or 30%. It's not very different. Here we don't see much, which is sort of surprising. So there are some ideas of how this could come about. In particular, there's mechanism for superconductivity due to Kohn and Luttinger, which basically says that every metal eventually is superconducting if it's not a magnet. And there's some more recent work from Steve Kivelson and collaborators in a couple of different contexts suggesting that actually the annular Fermi surfaces, or having two Fermi surfaces in the regime where that may help with this type of superconductivity, which usually is thought to be sort of, I think it's always thought, most experimentalists have always thought about this as just a totally theoretical curiosity where, it's fine, at a microkelvin everything's a superconductor, but it's not really experimentally relevant. But there's some theory work that suggests that maybe the transition temperatures when you have these annuli may become reasonable, with dimensionless couplings of 0.1, which is kind of similar to what we observe. So that is so these are, I think, all still viable theories at this point. We don't have a very a sharp answer. I think we can tell there's some different things. The one opportunity is the fact that the phase diagram here, even though it seems kind of complicated, maybe when you try to talk about it all in one talk, is much simpler than, for example, in the moire systems. And by the way, you're basically taking graphene, you're using interlayer coupling to generate a large density of states, and then all hell breaks loose, including superconductivity. Probably the mechanisms are closely related to those moire systems, even though symmetries are different and there are a variety of other aspects that may not be the same, but presumably the underlying mechanism is related. One idea that we are pursuing is to screen interaction. So you can use a van der Waals heterostructure to, for example, put a metallic plane very close, probably made of graphite, very close to the 2D layer, closer than the inter-electron spacing. This should lower the Coulomb repulsion by quite a bit, because if you have electrons 10 nanometers apart, but you put a metallic plane 3 nanometers away on both sides, you're essentially going to exponentially screen that repulsion. And so presumably you will suppress these types of stoner transitions down to lower density. You'll access higher density of states without symmetry breaking. So if it's phonons or some generic pairing mechanism, it should just get stronger. But of course, if the superconductivity just follows these stoner transitions and really depends on the distance from the stoner transition, then probably that would point towards magnetic fluctuations. I think, in unrelated work, we've also been developing ways to probe the thermodynamics of all of these things. So you can try to look and see, what the magnetic susceptibility is, for example, of these superconductors in van der Waals heterostructures, which is quite a difficult thing to do because, the number of electrons and, of course, the sort of sample volume of these things is tiny. And I think, it'd be interesting to look, for example, with STM at these proximal phases to try and understand what the symmetry breaking really is. Does it actually spin? Is there intervalley coherence? Are there other distortions that are occurring that we haven't thought of? And so I think this is kind of a nice platform because these samples are also highly reproducible. There's no uncontrolled twist angles. We have not actually measured multiple samples to look for superconductivity, but when we've looked at density of states, the phase diagrams of these magnetic states seem to be identical from sample to sample, down to relatively quantitative questions of, at what density and electric field does such and such a transition occurs. It seems to be the same every time. So this means now you can kind of play with this. I think, of course, you can look at other graphite allotropes because this general behavior is generic to graphite, really. It wouldn't surprise me if it turns out that just regular graphite appropriately measured is also a superconductor of a similar type. But you can also couple it to a variety of other things. You can add a moire, you can add transition metal chalcogenide cladding layers, which would turn on spin orbit, maybe give you access to things like FFLO states by sort of controllably turning on spin orbit. And of course, you can then try to think about in situ interfaces between superconductors and other things for various devices one might like to make. So anyway, with that, let me conclude with acknowledgements. In particular, let me call out Xuan, who just my soon-to-be former graduate student who just graduated and was responsible for this, and Ben Shea, an excellent undergrad who worked with him, and other collaborators far and wide. Sorry, this is out of date. I gave you the reference at the beginning of the talk. So thanks everybody, and yeah, I'm happy to take questions. Hopefully, you're all still here. I haven't heard anything. So.
Thank you, Andrea, for the exciting talk. I'll first ask the audience if you guys have any questions. Yeah, Walter?
Yeah, nice talk. Yes, very interesting. So I have a few simple questions about the magnetism, not the superconductivity.
Sure.
The first thing is, what is the Curie temperature?
Between 5 and 10 Kelvin.
Okay.
We haven't measured it carefully, but at 5 or 6 Kelvin, you already see many of the features and density of states.
Okay.
So we haven't looked at it. We haven't found a sharp transition that we can.
So that gives me a scale where.
Yeah. That gives you the scale. That's right. Yeah.
So so my second question was, you have these different sort of polarization effects, either value polarization or spin polarization, and I was wondering, does that have something to do with the ratio of inter-valley versus intra-valley scattering, and what are the sources of fluctuations or scattering that we have to think about? Is it electron-electron scattering, electron-phonon scattering, or?
Yeah, I think the short answer is yes to all of that. That's precisely the origin of those asymmetries. They are very hard, as far as I understand, to calculate from first principles. So what people have tended to do in related problems, and also in this problem, is more or less try to classify what the asymmetric couplings can be, and then try to work out what the phase diagrams of, and what are the relevant couplings. What if you run various RG calculations, for example? That's one thing where theorists have done a fair amount of effort, put a fair amount of effort. What are the different phases that you can get? And the answer is a lot of different phases, right? And so basically, one way that it was put to me was that measuring the ground state experimentally is about the best way and then sort of going backwards up the RG is the way that you can sort of guess what those couplings might have actually been. But there are a bunch of different couplings. They have exactly that type of origin. There's both electron-electron and electron-phonon, ones. And depending on which are stronger and, these initial conditions, at least in that sort of RG picture, which many people like to do, you get different ground states. But it hasn't been done very carefully for this system. Actually, it's been done more for bilayer graphene and monolayer graphene.
Okay, thank you.
Any other questions? Yeah, if not, Rehan.
Hi, thanks for the interesting talk. I have a question. So if you add moire to the system, do you still see this isospin transitions? How different would the phase diagram?
It's a great question. Yeah, it's a part of my talk I cut out. Let me find it again. Yeah, so you can add a moire, indeed, right? And the basic takeaway is that when you add a moire, the isospin stuff doesn't change much, right? And what does happen is that if you happen, so we have these, let's say, quarter and half metals that can occur without a moire. If your moire period happens to line up such that, for example, you're at nu equals 1 of the moire at a density where even without the moire you have a quarter metal, then you'll get a gap because you only had a quarter metal, so you just need 1 electron per site to be in a gap state. So I think that the way to think about it is that the energy hierarchy here is that Coulomb repulsion is larger than the moire potential, right? So you already break off you already gap out all your opposite other spin and valley flavors. You're left with one band, and then you have a weak moire potential, which will gap that out at the moire zone boundary. And then the same thing can happen for a half metal. And then there are interesting effects of Berry curvature and so on, but it's a very different type of, flat band limit than in twisted bilayer graphene, for example. Here, it's really, you just had large density of states, and most of the physics is driven by that. And then the moire is a small perturbation on top of that, which will allow you to have gapped states at commensurate fillings, which are hard to do, obviously, in no
you
moire
still
samples.
see those superconducting features?
We haven't looked actually, but carefully at moire samples to look for superconductivity. But I can't imagine that it wouldn't be there. And I suspect now that the superconductivity reported by, I was pretty skeptical of superconductivity reported by the group at Berkeley and Stanford. I'm a little less skeptical now. But I think that would maybe correspond to this SC2 within a moire system. But I think most of the physics, except for insulating states at finite density, appears also without the moire.
Thank you.
Okay, should I?
Thanks, Andrea, for the interesting talk. So for the negative compressibility, so that occurs, if I think of the energy scale, that occurs when the negative exchange or correlation energies dominate over the positive kinetic energy. Is that the case, right?
So they're kind of different. There are different scenarios where that can happen. So yeah, as a general background of negative compressibility, what you're saying is true. So that's why it tends to appear in like Wigner crystals, for example, in quantum Hall. But at first order phase transitions, I think there's a relatively, there it's really coming from just like domains in the sample and just totally non-uniformity of the sample, which I guess you could probably cast in the same language. But the sort of spikes in negative compressibility are really just coming from first order phase transitions between states that have different density at the same chemical potential, or different chemical potentials at the same density.
Thanks.
Okay, Andrea, I have not been following on the superconductivity in graphene very closely. Is it the first time people report like a superconductivity in trilayer system?
So without a moire, yes.
Okay.
Right. I think that this is the first time there's superconductivity in a non-moire, just basically regular graphene.
Yeah,
right.
okay.
And I will predict with great confidence that there are many other graphenes that are also superconducting. That superconductivity is pretty generic to these Van Hoff singularities in graphene systems.
Yeah. You did not compare the mechanism between these two systems, but what I got is so the superconductivity here has different origins related to magnetism, right? Perhaps it's different from the.
It may be different. It may be the same. I don't know, actually. Certainly all of the moire systems also have magnetism, right? I can speculate, right? my speculation is that they're kind of connected, but they're in quite different limits. But I don't know. I mean, I'm not sure the superconductivity here is connected to magnetism. I'm not sure that it's not all phonons. It's possible, right? And it's hard to say at this point, right? I think without there, and to some degree, right, that's a philosophical question, like what's the mechanism? Like it's not a sharp question. A sharp question is what's the pairing symmetry, but what's the mechanism is not really a sharp question. So I think an interesting question to try to answer here, and also in twisted bilayer and other related systems, is what is the pairing symmetry? Because after all, like if some of these turn out to be really exotic pairing symmetries, then that's much harder to get, if not impossible, with like a purely conventional pairing mechanism. So I think that's a type of sharp question that you can answer. I think, in so much, if one wants to ask what do I think is important about the results that I just showed you, I think that it's going to be easy to do more complicated experiments with these because the material is very clean, very regular, and highly reproducible. And that just has not been true for the Moiré systems because every sample is totally different, which is great if you want to write a bunch of papers, but it's terrible if you want to find the answer to anything. So yeah, that I think is going to be helpful here, is that, we can make a dozen of these samples. They're all going to behave the same way, which means we can make more complicated samples.
Okay, thank you. Sure, do you still have other questions? Oh, okay. Okay. Yeah, if there are no further questions, then let's thank Professor Young again for a very interesting, illuminating talk.
Okay, thanks for the invitation. Yeah, sorry I couldn't visit in person. Next time.
Yeah, in the future, yeah.
Yeah, bye.
Can I stop the recording? Xuan, do you want to continue your discussion with Andrea?
I'm happy to chat if
Yeah.
yeah.